What?
Let's try to do this. Yeah. Okay.
Good. So just switch the screen.
Oh, what happened? It disappeared.
Are they switching?
No, they count with like using the presentation that you sent. They can switch it like after you.
Yeah.
Oh, no, this.
Could you just switch the screen?
Because they can see it.
Make a duplication of the picture, not duplicate. Send to another monitor.
Is this the one you tried before? This one.
Let's do the back.
Let's just present.
Yeah. How do we close this? No, no. Which button?
These two, but just
Sure. Cool.
Okay.
But no,
that's a one. Let's just use.
okay, cool.
Doesn't say. Let's use those slides.
Yeah, sure.
It is.
Are they-
I'll point this out.
Okay. Okay. So, hello everyone. We're Cathie and Oleg. We're going to talk about ZKVM today, and I'm very excited to show this to you today. So we're going to start with me giving you an overview of how the architecture works, and then Cathie will take over and go into the juicy details of the architecture. Now let's start with the problem so you understand the motivation for this whole design. How do we make the financial or non-financial assets live on the internet? And more specifically, what we mean by this is how do we make these things ownable by computers? So this sounds a little bit strange, but this existed for over 100 years now with vending machines. And what's interesting is vending machine owns property in physical world, and it's not tied neither to the issuer of money nor to the creator of the products. So it's a fully decentralized system. So how can we have this for physical property but not for the digital one? So it turns out the biggest problem here is that we need to simulate this whole universe where those things of value could exist, and this is a tough problem. Now, every tough problem can be solved with enough of blockchain in it, so let's use a blockchain, right? What we mean by blockchain is we need to define the token, authorize transfers, and prevent double spends. And this sounds simple, although the problem is it's a pretty heavy task because every participant in this game has to verify these rules. And the value of this network is proportional or better than proportional to the number of users. So when you have a lot of users, everyone has to play the game, everyone has to verify this, so naturally you have these three technical challenges. How do you scale this? If everyone has to share the data, how do you protect private information? And how do you turn this into a platform on which you can build more interesting applications and protocols, preserving the scalability and privacy? So everyone here was wondering about these problems for a long time already, and there are excellent, great projects trying to address various problems here. So what we are trying to do with ZKVM is to pick some cool ideas and kind of try to reach the Pareto frontier of this problem set, covering all of these issues, but also keeping the solution pretty simple and nice. So how does this work? We start with a transaction model that is pretty simple. Everyone who is aware how Bitcoin works, it looks pretty similar. You have inputs, outputs, the value is transferred from inputs to the outputs, and transactions kind of form this chain of transfers. It differs from the Bitcoin model in two important ways. First of all, in ZKVM, you can issue arbitrary assets, so there is no one single coin that is built in. There are issuers, and they can create their own assets. And second point is that every transaction is not a hierarchical data structure that declares those pieces of information. Instead, each transaction is a program. And this program imperatively performs actions on the assets. It claims the input, creates an output, splits and merges value. So let's look a little bit deeper. In transaction, we have mostly the program. We have also zero knowledge proof and a little bit of metadata. And if we want to verify this, we instantiate the VM. So important thing here is this VM is stateless and instantiated for each individual transaction. And it has no side effects outside of its own contents, and it's thrown away completely after transaction is verified. And what happens in the program, it's a simple stack language that performs some operations on the assets and maybe some data. And these operations are kind of high level. They also allow the users to express some operations that they want, but also check the network rules. The whole network wants to make sure that the assets are not copied, that some other rules are respected. And this machine is pretty simple. It's not Turing complete by design. So it has a couple of side effects that are completely contained within the VM and recorded in transaction log and constraint system. So constraint system is a bulletproof constraint system that allows us to build the constraints on the fly. So as transaction is being executed, those instructions create constraints on the fly that both verify some network integrity rules, but also allow you to express custom rules within the contracts. And once the program is done executing, you have this constraint system built that is verified in one go with a single aggregated zero knowledge proof. Finally, after you've done verifying the proof, you have a list of effects the transaction created for the blockchain state. And these effects are such as claim unspent output, create unspent output, and these effects are applied to blockchain state separately. So this design allows you to do the parallel verification of all transactions and do this state update in a batch very efficiently. So we talked about how you can do the changes to the asset flow, but how do we authorize these changes? So we have this concept of contracts where the contract is an object that has arbitrary payload, like one or two or more items, and these items could be either values or parameters. So this is a flexible model to lock up more interesting state machines. And these items are protected by something we call a predicate. And also the contract is actually this thing that is UTXO in the UTXO set. It's a frozen contract. So when you have an input instruction, you actually claim that some output, one contract exists. And when you have an output instruction, then you freeze this contract in the UTXO set. So how do you use it? In the simple case, you use this predicate as a public key, so you provide a signature, and VM verifies the signature and unlocks the items for you. But you can also commit a predicate, like a program, into the predicate. And if you reveal this program can be executed, and VM first gives the chance for the program to take ownership of the items. Then the program can split the value or lock it in some interesting way or create some constraints, and then whatever is left on the stack is left to the outer program to execute. So this is done using a thing called taproot, which is designed by Gregory Maxwell and Peter Wheeler for Bitcoin. And it's a pretty clever design where the biggest idea is that most of the contracts are multi-party contracts that can be satisfied with in one of two ways. Either by cooperation or through a dispute. So if you have a cooperating parties, for instance, you have a payment channel and they cooperate to close the channel, then they simply can provide the aggregated signature, which looks indistinguishable from a single signature on the network. However, in case they don't cooperate, the party that is online and wants to close the contract, they can reveal the branch, one of the possibilities of the subprograms, and execute it to enforce the contract rules. So this reveals a little bit of information, but in ZKVM the data is encrypted, so even in this kind of worst case scenario, some privacy is preserved. Now, this is the entire instruction set of ZKVM, and you can see that these instructions are kind of high level, so you have instructions to do some high level operations on contracts, on values, you can issue, you can retire, you can mix and merge. You have instructions for the constraints, arithmetic and Boolean. And what's surprising is that this is very small instruction set. And there's no thing like you have a hierarchical data structure and some long list of checks that you have to do in your protocol. Instead, these network rules are embedded inside each instruction. And your transaction is pretty thin, it's just a program. So you have this very nice composition of network rules inside the instructions. And for comparison, our previous work on TXVM without privacy features was twice as big, and even Bitcoin and Ethereum are even larger instruction sets. So this is pretty cool. And at this, I'd like to leave it to Cathie to walk you through the kind of details of how this all comes together. Thank you.
Hi, I'm Cathie. I'm going to talk to you about some of the lower level cryptography. So let's start with the cryptography stack. At the very bottom, we use curve 25519 Dalek, which does really fast elliptic curve operations, and we use this for things such as checking signatures. And on top of that, Henry's ristretto group that he talked about earlier allows us to have a safe prime order group, and this is what we use to do our bulletproofs zero-knowledge proof protocol, proving and verifying. And on top of that, Henry, Oleg, and I implemented bulletproofs, which is a zero-knowledge proof system that we use to create all of the proofs of correctness. And now we're getting closer to the ZKVM layer. On top of bulletproofs, we made the cloak protocol, which is a protocol to enforce confidential asset transfer. So basically it keeps the asset types and asset amounts secret while enforcing that assets can't be created or destroyed. And so those are what Oleg means by network rules. And then on top of that, we also want to give people the ability to make custom rules for their own smart contracts. And so you have custom constraints, and you can build these using the R1CS API for bulletproofs. So on top of all of this, we have the instructions that Oleg just walked you through. And these are arithmetic and Boolean operations that then translate to cloak and constraint operations. And on top of all of that, you have your protocol. So you can use the instructions within your protocol to build vaults, payment channels, order books, or whatever else you want. And a nice aside is that all of our part of the stack is built in Rust, and so it's really easy to read and has really clean APIs. Cool, so here's an example of a custom constraint that you can add, for instance. So in this statement, you say either p equals b plus r times t or x equals y. And then on the bottom is what this constraint would look like within ZKVM using the ZKVM operations. So as you can tell, it's a stack-based language. So it's not too difficult to translate. And more generally, when you're making a constraint, this is the workflow. You start with some data, and that data gets translated to variables. So these variables are basically the internal bulletproofs variables that represent commitments, blinded commitments to this data. And then you can translate those variables to expressions and then to Boolean constraints. And those Boolean constraints will then be added to the constraint system when you call verify on them, and they'll be turned into multiplicative and additive bulletproof style constraints. And so you don't actually have to deal with any of that transformation yourself, and it all gets taken care of sort of behind the scenes for you, which is hopefully a really nice user experience. So here's an example of if you wanted to build a custom constraint that takes in, build a custom smart contract that takes in some data adds constraints to them, and then spends that amount. So first you take in data by pushing to the stack, you turn that into a variable, you add some custom constraints to that variable, so you can say it has to like satisfy some properties based on other inputs, and you add that to the constraint system by calling verify. So now that you have a variable that represents your input, now you want to spend it. And so what you do is you call this borrow instruction, and borrow creates two values. It creates a positive and negative value. And the positive value becomes the value that is output from the transaction. And the negative value gets added to this cloak. So once again, cloak enforces confidential assets, so no value is created or destroyed. And so you have cloak taking in this negative value and also taking in the variable that was initially created and making sure that it doesn't, that those two balance out. So that's an example of a whole workflow for making a custom constraint that spends a input, checks some constraints on them, and then creates an output. As you can tell, these contracts actually imperatively express the requirements. So this gives us a nice security guarantee, and you avoid this whole class of security bugs like the confused deputy problem. So you may be wondering, what are the confidentiality guarantees of this scheme? So there's sort of two parts to confidentiality. First is data security. So this is pretty straightforward. All data is encrypted by default. So anything that gets turned into a variable is a blinded commitment to that data. That includes account identifiers, asset quantities and types, and contract parameters. And then contract logic is protected by taproot, which Oleg mentioned earlier. The privacy story for this is that if all of the parties cooperate, you only have a single signature, and that doesn't reveal anything about the parties or the conditions. In the case of a dispute, only a specific branch is revealed, and so you can see the logic that is being disputed, but that doesn't actually reveal the data underneath. The data is still blinded. And then in terms of data flow security, we made a design decision to use a UTXO set, and so that means that the transaction graph is public. This allows us to use UTXO, which is a scheme by Taj from MIT, to do very efficient compression of UTXOs. Now within a transaction, asset flow is fully hidden thanks to cloak. And there's an interesting sort of incentive to actually aggregate a lot of transfers within one transaction, because the larger your transaction is, the more efficient it is to prove, to store, and to verify. And that's because of the efficient inner product argument thanks to bullet proofs. And so we designed it such that there is a high incentive to aggregate transfers, and that therefore increase both security and performance. So in terms of performance, bulletproofs allows this to be very fast, and along with the vectorized implementation of curve to 5519 and our signature aggregation protocol, we use MuSig. So we have under 1 millisecond per output, and up to 1,000 transactions per second if you do batching. It's always fast regardless of your custom constraints. And this is because range proofs are really the expensive part of the operations. And so your custom constraints are actually really cheap, because they sort of get added onto this logarithmic size bulletproof proof. And it scales with privacy, as I mentioned earlier. As you aggregate more transfers into a transaction, you save both space and time. You get effectively free storage. Thanks to UTXO, the cost of storing the UTXO set is close to negligible. And then lastly, it is SPV friendly. So in conclusion, ZKVM is something we've been working on for a long time, and we've actually been building the entire stack from the base up, and it allows for a multi-asset blockchain that scales, protects data and on-chain, and provides programmable constraints so you can have custom protocols. This is a project that is open source. It's available under the Stellar repo on GitHub, and there's a lot of work that's gone into both ZKVM directly and into previous work, such as Chain's work with TXVM prior, and all of that can be seen at the related projects URL here under Interstellar. Cool, so that's it from me and Oleg. These are our Twitter handles if you have any questions, And the project Slingshot, which is sort of the parent project to ZKVM, is sponsored by Interstellar and the Stellar Development Foundation. Thanks. Any questions?
Hi, so you mentioned that some privacy could be lost in the event of a dispute. Do you have any provable guarantees on like what guarantees you have, I guess?
Do you want to talk about taproot?
Oh, sure. So guarantees are pretty simple. You know your contract, you know what you expose on the network. So if you have a specific clause that says you have to pay a certain amount to a certain address, provided some conditions, then you know that exactly the formula, relationship between all the parameters is revealed on the network. And then you as a user, it's kind of pushed to the kind of user level from the consensus layer. You know that if you're using a standard formula, let's say for everyone is using payment channels, then your transaction is now slightly distinguishable from everyone else, but it's just the same as any other forced payment channel closure. So you have this direct visibility into what you're revealing, and you have strong guarantees about specific parameters. So you completely hide the asset type and asset amount.
Thanks. This looks really exciting. So some of the scaling and privacy benefits had to do with batching. Does that batching require the cooperation of people signing the transactions? Or a flip side question is, if you have many separate independent parties issuing transactions, do you lose some of the performance benefits?
Yeah, so what we mean by batching, and I'll go to, I don't remember where the slide is if you have a bunch of, if you have 2 inputs and 2 outputs and someone else has 2 inputs and 2 outputs, you can merge that into one transaction and one proof. And so that does require cooperation. It doesn't require trust. You don't have to share your secrets with the other people that you're batching with, but you do have to cooperate and be online and do some rounds of communication. And so yeah, as you said, if you don't have cooperation between parties, you don't get the batching scaling benefits.
So you could have an online protocol where participants show up and they're not exposing any confidentiality, they're not violating their confidentiality to participate?
Yeah, exactly. So actually, as a demo of this concept, we implemented the batching functionality for the bulletproofs range proofs, and that's just a multi-party computation protocol in which you just do several state transitions with other parties. And the only thing that you have to trust for the other parties to do is not go offline, because if they go offline, then your whole protocol has to start over. So that's the only thing you reveal or trust.
There's one extra thing. So even if you have separate transactions and you have a whole block of them, you can still, you don't save on bandwidth because they're not aggregated, but you can still dramatically save on verification time because you can batch verify all the cryptography. And specifically within one transaction, all the crypto operations are fully deferred and batch aggregated for transaction, so that you don't pay for individual Schnorr signature verification or individual taproot commitment opening. All the instructions in the program, they're super cheap. It's like parsing some data format. And if they do some crypto operations, those are deferred and batch verified in one go in the end of the transaction verification. And you can batch them further across transactions to have even more dramatic savings.
One last, can you explain my shirt to me after this?
Yeah, it's the same shirt as this.
Oh, yeah, okay, good.
It's a great talk. Sufficiently few people understand, appreciate the importance of confused deputy, but yet you mentioned it up there. I was wondering if you can say more about it and where it shows up and what you do about it.
I feel like that's more your designs.
Okay. So the thing is, you know how Steve Jobs was showing the iPhone and saying, oh, you can now touch your music, right? So you can touch your digital assets because you have this programming environment where you have the direct operation on the values as first-class types. So, for instance, in Ethereum, if you want to design custom types, you have to create a little banking application where you move numbers. Here, you issue a thing, and you move this thing, and VM prohibits you from copying it or from dropping it. So that's one part. And it's actually pretty cool that I learned that the Facebook coin has this similar idea. They have this VM, but also first-class resources, so it's kind of similar thing. And the contracts, they implement something like object capabilities pattern, where you the only way to get into the contract data, you have to satisfy the contract, like go through its API. And together, it means that your logic can be imperative and very straightforward. So with this borrow instruction, if your contract says, oh, I want to receive a payment of $5, you don't receive some value object and inspect its value or like have a proof about its value. Instead, you just say what you want. You say, I want $5, I just created, borrow with 0 interest rate. And you send it where you want to go, and then you just leave the negative amount on the stack, and now the user has to deal with it. And the user cannot drop it, so they have to find the appropriate positive value and combine this. So everything's pretty straightforward and simple to, like easy to reason about.
Thank you.
Thanks for the talk. As a taproot model, does it require a small subset of participants in the contract, or can it be extended to like large number of participants where we operate on partially public and partially private data?
Yeah, it's designed to be either a small or large number of participants, and Oleg talked in his half about taproot and how you can basically have a tree of contracts that people can participate in, and you can, they're by default private.
So how will it work for a large number of participants? Will we just have a very large tree with like lots of contracts participating, or so anybody can join at any time without permission from others? Or like, can you explain a little more?
It requires interactive setup. So if you have millions of participants, that's probably not going to work out. Okay. So the cryptography is pretty simple here. There is no like magical, like kind of giant accumulator going on.
So we cannot implement something like maker CDP opening or like some Uniswap or something like this.
Oh, you may try and we'll see the results, but I'm not sure it will be like.
Okay, thank you.
Yeah.
I noticed on the slide describing taproot, and that the expression there was the public key, which is k times the base b, plus some hash times base b. Is that because those are the same bases? Is there not potential for confusion between the key and the hash?
Well, the hash is hash to scalar, and yeah, the bases are the same, so you can sign for this whole root, and the hash is just an extra known scalar to the parties. But it's still a strong commitment, so when you reveal the branch, the program, you reveal all the surrounding components. And if you want to make sure that this thing is not signable, then like if, for instance, we're having a contract where we want to ensure only programmatic opening, then we choose the key with a secondary base, so this whole like root is unsignable. And it's not allowed to sign for anything but the root. So you either open up the branch or sign for the whole root. So that's why the bases are the same. The bases are the same if you want to sign for it, but the key part would have a different base if you choose to kind of just delete it from the...
So the bases have to be the same in order to be able to either sign the key or for the hash. Okay.
Yeah.
Thank you.
You mentioned that a transaction have side effects, and we know that different transactions can have conflicting side effects. And the question is, if we try to batch in transaction which have conflicting side effects, can it be a good strategy for the DOS protocol for running big size of computational, and it can like stop protocol because you all time will get protocol will fail because your transaction which you try to batch will get error or something like this. Is it possible way to DDoS protocol or not?
So if I understand correctly, you're asking if you can have a protocol in which you do batch transactions, but you have some kind of way to check if there's conflicts between the transactions to see if you can batch them first?
Yeah. I mean, do we need to run do we need to run this heavy zero knowledge computational or we can check is we have conflict in transaction before?
Oh yeah, so if you were to try to batch like two transactions or two transfers, I guess, what you would do is you'd have to cooperate. It would be like a multi-party computation protocol if you're batching the proving. And so I guess what would make sense is you first share what the expected output, like the expected side effects are, and then if those conflict, then you don't batch.
Okay, thank you.
Yeah.
Hi, my question is about scalability. So you mentioned signature aggregation and taproot, which is great for smart contracts. And you also mentioned UTXO, which is very good for storage. But in my understanding, the bandwidth limitation, the actual scalability problems that most blockchains have are still in terms of bandwidth, data propagation over a global network, and the initial block download. And you still have the proofs that are 1.5 kilobytes. So how would you say that the ZKVM compares to, for example, Bitcoin when it comes to actually scaling for 10 or 20 transactions per second over a global network of full nodes, like fully validating nodes?
Yeah, so you're right to note that the bandwidth is the last kind of linearly growing problem. And so the good news is it's like in absolute numbers is pretty decent. It's like 40 megabits for the topped out 1,000 transactions a second. So it's not impossible, but for the mobile devices, it's not good. And that's why the SPD mode is here. And on a mobile device, you really want to be first-class citizen without depending on a specific server, without losing your privacy. So you want to track the chain and watch for payment channel updates or updating your UTXO proofs. And for that, you only need the block headers and a little bit of Merkle tree branches for the UTXO. You don't need all these transactions to verify. So you can dramatically say.
Right, but that's the same way as in Bitcoin, right?
Yeah.
So my question is compared to Bitcoin, does this scale worse or does it scale better? And if so, on what order of magnitude? I'm coming to the conclusion that it's about 5 times worse than Bitcoin because you have the bigger proofs.
So there are two advantages. UTXO allows you to have very compact state. You don't have to have the whole UTXO set. And second, you can bootstrap from the checkpoint committed to the blocks. So you have network verified state that is consensus, everyone agrees on, and you can bootstrap from this recent checkpoint. You don't need to replay all the blocks to arrive to it. So there's
okay, so there's some kind of checkpointing involved as well.
Well, all the block signers or miners, however you use it, they agree on the actual commitment to the whole state, and this is written to the block. So you can just bootstrap from the recent one.
But that's a different security